The experiments we're going to do in this film have to do with vorticity. They illustrate the concept of vorticity in a physical way, and they also show how vorticity can be useful in understanding. Let's begin by remembering that the vorticity is a measure of the moment of momentum of a small spherical fluid particle about its own center of mass. Suppose that you had some very complicated motion in a liquid, and that it were possible, by magic, suddenly to freeze a small sphere of that liquid into a solid. During the freezing, the moment of momentum would be conserved. And so it turns out that the angular velocity of the solid sphere, just at the moment of its birth, is exactly half the vorticity of the fluid before freezing. Now, the dynamical theorems of Kelvin and of Helmholtz relate the changes in vorticity of a fluid particle to the moments of the forces acting on that fluid particle. The vorticity omega is defined as the curl of the velocity vector. Each fluid particle has a certain vector vorticity. The whole fluid space may be thought of as being threaded by vortex lines, which are everywhere tangent to the local vorticity vector. These vortex lines represent the local axis of spin of the fluid particle at each point. In two dimensions, the vorticity is the sum of the angular velocities omega A and omega B of any pair of mutually perpendicular fluid lines AA and BB passing through the point in question. In a rigid body, every line has exactly the same angular velocity, so the vorticity of a rigid body is the same at every point. It is exactly twice the angular velocity. This gadget is a vorticity meter, which floats in water with its axis vertical. The two vanes at the bottom are driven by the angular velocities of two mutually perpendicular fluid lines. So the arrow at the top turns at a rate equal to the average of these two. That is, with half the vertical component of vorticity of the lump of water in which the vanes are immersed. This tank has been on the turntable for a long time, and viscosity has forced the water into a rigid body rotation. The vorticity float rotates almost exactly with the speed of the crossed white lines on the bottom of the tank. Sometimes the word rotation is used as a synonym for vorticity, but this does not mean that a flow has to be curved for vorticity to be present. Here, for instance, water flows in a straight channel. The streamlines are essentially straight and parallel to the side wall. But the arrow rotates, showing that vorticity is present. Near the wall is a viscous boundary layer, in which the velocity increases with distance from the wall. Let's look at a fluid cross. One leg moves downstream parallel to the wall, while the other leg rotates because of the non-uniform velocity distribution. So there's a net vorticity, and the vorticity meter spins. On the other hand, the flow may be without rotation, even though it is curved. This is the plan view of a spiral vortex tank. Water passes from the reservoir through a flow straightener and into the tank through a tangential entry. It spirals round and round in a very tight vortex and finally leaves vertically through a drain in the center. What will the vorticity meter do? It doesn't rotate. It moves in pure translation, like the needle in a compass box mounted at the rim of a rotating turntable. Let's look at a fluid cross as it goes round the vortex. Leg A follows the streamline, so it rotates counterclockwise. The angular momentum of the fluid is conserved as it flows toward the drain, so the tangential velocity varies inversely with the radius. This means that the velocity of the inner part of leg B is greater than the velocity of the outer part, and so leg B turns clockwise. The clockwise turning rate of B is just equal and opposite to the counterclockwise turning rate of A, and so the net vorticity is 0, and the vorticity float confirms this. Incidentally, since the two veins of the float are rigidly connected, the float does not respond to the shear deformation of the two fluid lines, but only to their average angular velocity. There are several theorems which relate the vorticity to the dynamics of fluid flow. One of these is Crocco's theorem, which is nothing but a special form of the dynamical equations of motion. With steady motion, if the flow is incompressible, if there are no viscous forces, and if only conservative body forces are present, then the vector product of the velocity vector with the vorticity vector is equal to the gradient of the stagnation pressure divided by the density, where the stagnation pressure, or as it is sometimes called the Bernoulli number, is the sum of the static pressure and the dynamic pressure and the pressure associated with a body force field. Consider a two-dimensional flow in the plane of the paper. If the flow is two-dimensional, the vorticity vector is normal to the paper, while the velocity vector lies along the streamline. According to Crocco's theorem, the gradient of stagnation pressure is normal to both the velocity vector and the vorticity vector, that is, in this direction, and in the plane of the paper. So the stagnation pressure, P0, is constant along each streamline and varies between streamlines only if vorticity is present. To illustrate, look again at the straight boundary layer. The pressure is uniform across the boundary layer, but the velocity is variable, and so the stagnation pressure is variable. This means that vorticity is present. The velocity gradient is strongest near the wall, and so is the gradient of stagnation pressure. In this run, with the vorticity meter near the wall, the rate of spin is quite large. Here, with the vorticity meter further out on the boundary layer, the rotation is less. And here the float is outside the boundary layer and is not spinning. As it moves downstream, however, it enters the boundary layer, which has grown thicker, and finally begins to turn. When the vorticity is 0, as in the spiral vortex tank, Crocco's theorem says that the stagnation pressure must be everywhere the same. The spiral of the vortex is so tight that it is not much of a liberty to think of the streamlines as being concentric circles. The equilibrium between the net pressure force acting on a fluid particle and the centrifugal force requires that the velocity v vary inversely with the radius r if the total pressure is to be constant throughout. This velocity law is exactly the condition required for the free surface to be a hyperboloid. Now the flow is being decreased, and you can see that the hole in the core doesn't really extend downward indefinitely. The infinite velocities and shear rates theoretically at the axis are undone by large viscous forces which come into play there. But as we increase the speed again, the vortex strengthens, and the bottom of the hole drops out of sight. An irrotational flow may contain singular points, where the vorticity is infinite. In the spiral vortex flow, a highly concentrated vorticity exists right at the center. Look at a fluid cross right at the center. Only at this point do both these arms rotate in the same direction. Now we come to a new idea, the circulation. Remember that the circulation gamma around any closed curve C is defined as the line integral of the velocity v around the curve. Now the circulation theorem relates the circulation around any closed curve C to the vorticity passing through any area bounded by C. Specifically, the circulation gamma around C is equal to the flux of the vorticity vector omega through the area bounded by C. So if there is a definite circulation around some curve, then the enclosed fluid must have vorticity. But if the circulation is zero for every curve in a certain region, then the fluid in that region must be entirely free of vorticity. Sometimes the vorticity is everywhere in the fluid, distributed throughout. But often the vorticity is very large in a thin thread of fluid, while the remaining fluid is without vorticity. Then we can simplify our thinking by lumping all the vorticity into a concentrated vortex core around which the fluid spins, and then by pretending that the remaining fluid is entirely free of vorticity. The vorticity is infinite in the core, because a finite amount of vorticity has been dumped into zero cross-sectional area. Now let's look at the circulation for a small circuit in the straight boundary layer. Because of the distribution of speed, there is a net circulation, which is in fact related to the vorticity of the enclosed fluid. In cross-section, a single vortex line with non-vortical fluid outside appears as a point around which the fluid moves in concentric circles. The velocity varies inversely with radius. In the solid body rotation tank, the vertical vorticity is everywhere equal to twice the angular velocity of the tank. Every horizontal circuit you draw has a circulation equal to the flux of vertical vorticity through the area bounded by the circuit. In the spiral vortex tank, the flow is non-vortical, except for the concentrated vortex core, which accounts, so to speak, for the whole motion. All fluid circuits surrounding the core have the same circulation because they contain the entire vorticity flux. All fluid circuits not surrounding the core have zero circulation because they contain no vorticity flux. A wing generates lift because of the higher pressure below and the lower pressure above. According to Bernoulli's theorem, the velocity on the upper surface must be greater than the velocity on the lower surface. This means that there is a net circulation around a lifting wing. Often we pretend that this circulation is produced by a vortex, which is bound in the wing, and which accounts for the circulatory movement. We don't care whether the vortex is really there. We care only about the circulatory velocity field that it creates. The circulation is important because of a powerful theorem which Lord Kelvin evolved from the dynamical laws of motion. This states that the time rate of change of circulation for a fluid line of fixed identity is governed by the torques produced by all the forces acting in the fluid. The torques due to the pressure forces, to the body forces, and to the viscous forces. Let's look first at the torques due to the viscous forces acting on a fluid particle a fixed identity. You can see from the force diagram for this fluid particle that the viscous forces can produce torques about the center of gravity, the center of mass. These torques are capable of changing the vorticity of the fluid particle, and thus the circulation. Here in the straight channel, the vorticity float moves downstream without turning because it is outside the boundary layer. But as the viscous layer diffuses outward from the wall, the fluid in which the float travels finally reaches a position where viscous forces create a circulation, and with it, vorticity. Here again is the tank on the turntable, with no motion and with no circulation. Now the turntable has started, but the fluid in the middle doesn't move because none of the agencies which create circulation have yet come into play there. Next to the wall, however, the fluid does circulate because of viscous stresses. These viscous forces gradually diffuse outwards from the wall, and more of the fluid circulates. In the end, viscosity brings all the fluid into a perfect solid body rotation. At this point, paradoxically, the viscous forces have vanished altogether, and there is nothing to force further changes in circulation. Now the turntable has stopped, but the motion continues unchanged, except near the walls of the tank where viscous forces act. The retarding viscous torque diffuses inward and decreases the circulation more and more until finally the whole fluid is at rest. When a fluid flows around a sharp edge, viscous forces in the boundary layer produce a separated flow. The fluid which has been affected by concentrated viscous forces forms a concentrated vortex. We can make the strength of a vortex visible by a ping-pong ball which remains in the dimple. The rate of spin, though, decreases because of viscosity, which spreads the vorticity of the core into the surrounding fluid. Now let's look at the body forces G as a circulation changing factor. If these are irrotational, that is conservative, this term is zero. But for rotational body forces, that is non-conservative forces, this term is generally not zero. Look at this small circular piece of fluid. If the net body force G passes directly through the center of gravity, this force produces no torques to change the circulation or the vorticity. Centrally directed forces like gravity are of this type. They are irrotational. There are two important rotational forces which change circulation and vorticity: Coriolis forces in a rotating reference frame and electromagnetic forces due to the flow of an electric current at an angle to a magnetic field. In both these cases, the line of action of the body force need not go through the center of gravity of a particle. Because of such forces, the oceans and the atmosphere are full of vorticity, and so are magnetohydrodynamic flows. Does the vortex in the bathtub always turn in the same direction? Does it depend on which hemisphere you're in? You can't really tell in the bathtub. The Coriolis forces due to the Earth's rotation are incredibly small, only about 1/1000th the force of gravity. But we've built an apparatus in which this is the dominant force. This large circular tank has a very small drain hole in the center. The tank is being filled with water, swirling clockwise. Remember, clockwise. We waited a day to let the motion die down. Now the clock has started, which means that the plug was pulled from the drain hose. This is a small vorticity float with its vanes entirely submerged. For several minutes, nothing much happens. Let's imagine that this is the drain. The water flows radially inward from all directions. The Coriolis force acting on the particle in the northern hemisphere as it moves radially inward is circumferential and counterclockwise. This force, integrated around a circle, contributes a counterclockwise torque in Kelvin's theorem. This tends to make the circulation increase with time counterclockwise. In the reference frame of the Earth, a fluid circle, which starts at one radius with zero circulation, acquires, or should acquire, counterclockwise circulation as time proceeds. Now, back at the tank again. At 9 minutes, there is still no perceptible motion. But at 16 minutes, we begin to see a distinct counterclockwise motion. At 24 minutes, the slow turning of the Earth has been enormously amplified. Although the Earth's Coriolis forces are very small, they are extremely important to our everyday weather. They can also generate hurricanes. If the conditions of temperature and humidity are such that there is a strong local updraft of air in some region, air must rush in from the sides and up the updraft. This is nothing but the water tank experiment upside down, and a strong vortex is formed. The third circulation changing factor is the torque due to pressure forces. Incidentally, if the fluid is incompressible, this term is zero, and so it cannot change the circulation. To think about this physically, let this be a small fluid particle, and let these be the lines of constant pressure in its neighborhood. The pressure forces acting parallel to these lines exactly cancel each other, and so the net pressure force must be perpendicular, passing through the geometric center. Now let these be the lines of constant density in the fluid particle. If the density lines are parallel to the pressure lines, we call this a barotropic situation, the center of gravity of the fluid particle must lie on the line of the pressure force, so the pressure force produces no torque about the center of gravity. But now suppose that these lines are tilted. So, then the center of gravity of the particle lies on this diameter, and if the density is variable, the center of gravity will no longer lie on the line of the net pressure force, so that this force may produce a torque about the center of gravity, and in that way change the circulation. In a fluid at rest, the lines of constant pressure are horizontal. Since the circulation is forever zero, the lines of constant density must coincide with the lines of constant pressure. That is why the interface and the free surface are also horizontal. If we tilt the interface, it does not remain tilted, as it does in this photographic illusion. The constant pressure lines and constant density lines are now misaligned, and the pressure forces in Kelvin's theorem create a circulation which rectifies the situation. The circulations in natural convection systems are driven by the pressure forces in Kelvin's theorem. One example is the hot water heating system of a house. Another is the principal circulation of the Earth's atmosphere between the cold regions at the poles and the hot regions at the equator. Kelvin's theorem also shows us how irrotational flows may arise. Suppose that you have a motion which begins from rest. If there's no motion, there's no vorticity, And if there's no vorticity, there's no circulation. Suppose, too, that the fluid is barotropic, and that the body forces are conservative, and that viscous forces are negligible. Then the circulation will forever remain zero, and so the vorticity will forever remain zero. The resulting flow is therefore irrotational. Suppose, for example, that an airfoil begins at rest and moves through the fluid. Circulation on all fluid elements is zero to begin with and remains zero, so that the flow remains irrotational everywhere, except in the thin viscous boundary layers where vorticity is produced by viscosity. It is a curious fact that viscosity helps generate lift on an airfoil. Here is an airfoil at rest, with no circulation anywhere. When it begins to move, viscous effects near the trailing edge result in the shedding of a vortex, and thus to a circulation on this curve. But the fluid along this larger curve has not experienced viscous forces, and Kelvin's theorem tells us that the circulation on this curve must be zero. This requires, though, that there be along this other curve surrounding the airfoil a circulation equal and opposite to that on the curve surrounding the vortex. This circulation around the airfoil, which may be ascribed to a fictitious vortex bound in the airfoil, is necessary for the production of lift. Now, when the airfoil stops, the bound vortex is shed as a stopping vortex, again because of viscous forces at the sharp trailing edge. On a circuit around either vortex, viscosity has acted and circulation is present. But on a circuit enclosing both vortices and passing through fluid on which friction has never acted, the circulation remains zero. Thus, the equal and opposite vortices produce zero net flux of vorticity through the entire bounded area. When all the torque-producing factors in Kelvin's theorem are absent, fluid dynamics can be given a beautiful geometrical interpretation in terms of Helmholtz's vortex laws. First, vortex lines never end. They formed closed loops, and the circulation is the same along the length of the loop. Second, a fluid line which at one instant of time is a vortex line will forever after remain a vortex line. Third, on a vortex line of fixed identity, the ratio of the vorticity to the fluid density and the length of the line remains constant as time proceeds. We can illustrate these laws by some experiments. Here are two vortices of equal and opposite strength. They move downwards together. The induced velocity of A moves downward the fluid at B, and vice versa. Each vortex core is convected with the fluid to which it is frozen. Smoke rings also illustrate the vortex laws. You've never seen a smoke ring which is broken somewhere, nor will you ever see one, because vortex lines can never end. The fact that the smoke ring propels itself shows that the vorticity is locked in the fluid, for each element of fluid is propelled forward by the induced velocity of all the other elements of the vortex, and so the whole vortex is convected by itself. The smoke, which after all marks the fluid, is carried with the vortex, again showing that the vorticity is frozen in the fluid. So, as you see, old vortices never die. They only fade away through viscosity. As a vortex ring approaches a wall, it spreads out and slows down. This may be explained in terms of the induced velocity field of the fictitious image vortex on the other side of the wall, which in effect takes the place of the wall itself. This sketch shows the vortex system for a wing of finite span. The circulation that is required for producing lift is created by a vortex bound in the wing. But this bound vortex cannot simply end at the wing tips. The vortex loop is closed by trailing vortices and a starting vortex which is left at the airport. We can make the trailing vortices visible in this apparatus. The camera looks upstream at the trailing edge of the wing. Behind the wing is placed a fine wire grid on which are mounted wool tufts. These wool tufts line themselves up with the flow. The angle of attack of the wing is being increased, and the tip vortices grow in strength as the lift, the circulation, and the strength of the bound vortex also increase. This little vorticity meter shows streamwise vorticity if it is aligned with the flow. It is not a propeller because it turns only if the flow is spinning. If we put it behind a wing, right behind the tip it spins fast. Slightly inboard or outboard, it hardly turns. The trailing vortex is strongly concentrated at the wing tip. The concentration of the trailing vorticity in strong tip vortices results in very low pressures in the centers of these vortices. When this occurs strongly enough in marine propellers, the water in the vortex cores boils and makes the trailing vortices from the blades easily visible. Looking at the induced velocity field of the vortex loop, you can see that there are downwash velocities within the enclosed region. These downwash velocities, which you can see in the tuft pattern behind the wing, act at the wing itself. They make the wing appear to be flying through air which is itself descending, and this results in what is called induced drag. The work of the forward-moving wing, as it moves against this induced drag force, accounts for the kinetic energy being stored in the constantly lengthening trailing vortices. Have you ever wondered why migrating birds fly in formation? One explanation, a plausible one, is that each bird takes best advantage of the upwash velocities and the trailing vortex systems of the ones forward of it. So each bird behind the leader flies on an ascending air current. You should keep in mind that the vortex laws come from the ordinary dynamical equations of motion. So anything you learn from the vortex laws can also be found by thinking about the pressure field. With the lifting wing, for example, air can leak around the tip from the high pressure region to the low pressure region. This leakage produces a transverse flow which accounts for the tip vortex. To show the effect of stretching vortex lines, we have an apparatus in which water flows over a hump. The water depth first decreases and then increases. The speed of the water is inversely proportional to the depth, and so the flow accelerates as it goes up the hump and then decelerates as it goes down the hump. Now I'm making a vortex with a sharp-edged plate. This vortex has its axis vertical. As it goes up the hump, the length of the vertical vortex line decreases, and so the vorticity decreases, as you can see by the spin. When the vortex line goes down the hump, the length of the line increases, and the rate of spin also increases. The effect going down the hump, however, is not as strong as the effect going up the hump. That is because viscosity is always acting to decrease the rate of spin of the ping-pong ball. When a vertical thread of fluid moves up the hump, its length decreases, but the volume of the thread remains the same, and so its diameter must increase. This also increases the radius of gyration. To conserve the moment of momentum, the rate of spin must decrease. Now, when the vertical thread of fluid goes down the hump, it stretches and becomes thinner. Therefore, the rate of spin must now increase. A figure skater does the same thing. She speeds up by decreasing her moment of inertia. Turbulent flows are full of vorticity. The vortex lines are like tangled spaghetti. The mutually induced velocities of these vortex lines causes some of them to lengthen, and this lengthening produces a finer grained turbulence with higher velocity gradients. This makes for added viscous dissipation. Big whirls make little whirls, which feed on their velocity. Little whirls make lesser whirls, and so on to viscosity. In this open channel, water flows around a bend. Upstream, the flow is parallel to the walls of the channel. Because of the boundary layer on the bottom of the channel, the upstream flow has a horizontal component of vorticity in a direction transverse to the flow. But upstream, there is no vorticity component in the vertical direction, nor in the streamwise direction. Now I am putting in the little streamwise vorticity meter at the end of the bend. Somehow, a streamwise component of vorticity has been generated in the bend. To see why, let's look at three perpendicular fluid lines, A, B, and C, in the upstream position. If we neglect viscous forces compared with inertial forces in the bend, we may imagine the vortex lines to be frozen to these three fluid lines. Notice, though, that there is no vertical component of vorticity C, nor any streamwise component of vorticity B. There is only a transverse component of vorticity A, associated with the viscous boundary layer on the floor of the channel. Now line C moves along the center streamline to position C prime, so there is no vertical component of vorticity C prime. The vertical component of vorticity is connected with the turning of the lines A and B. Line B follows its streamline and therefore rotates in a counterclockwise sense. Since the vertical vorticity remains zero, line A must rotate clockwise by an equal amount. This clockwise turning of line A into position A prime requires that the velocity at the inside of the bend be greater than the velocity at the outside. The important point is that the vortex line A prime now has two components. One component transverse to the flow, which we had before, and a new component along the flow, which we did not have before. This new component, which is called the secondary vorticity, is what causes the water at the surface to move from the inside toward the outside of the bend. And these heavy oil droplets, which move along the floor, show that the flow on the bottom moves toward the inside of the bend. Such secondary flows often occur when a channel is curved. When a river goes round a bend, the secondary flow erodes the outer bank and deposits sand and pebbles on the inner bank. This tends to make the bend get more bendy. Some people think that this is one of the mechanisms by which exaggerated cases of meandering occur. When a pipe is curved, there are two cells of secondary flow. These secondary flows carry high-energy fluid from the middle of the pipe to the wall, in this way increasing the frictional losses. The vortex laws are also illustrated by the flow in this long channel as it goes under a circular cylinder. Strong vortices are developed from the vorticity present in the viscous boundary layers on the two side walls. Suppose that this thread of fluid coincides with one of the vertical vortex lines. As it moves downstream, it is both bent and stretched. The stretching of the vortex line intensifies the vorticity and makes the vortex core visible. The experiments we're going to do in this film have to do with vorticity. They illustrate the concept of vorticity in a physical way, and they also show how vorticity can be useful in understanding. Let's begin by remembering that the vorticity is a measure of the moment of momentum of a small spherical fluid particle about its own center of mass. Suppose that you had some very complicated motion in a liquid, and that it were possible, by magic, suddenly to freeze a small sphere of that liquid into a solid. During the freezing, the moment of momentum would be conserved. And so it turns out that the angular velocity of the solid sphere, just at the moment of its birth, is exactly half the vorticity of the fluid before freezing. Now, the dynamical theorems of Kelvin and of Helmholtz relate the changes in vorticity of a fluid particle to the moments of the forces acting on that fluid particle. The vorticity omega is defined as the curl of the velocity vector. Each fluid particle has a certain vector vorticity. The whole fluid space may be thought of as being threaded by vortex lines, which are everywhere tangent to the local vorticity vector. These vortex lines represent the local axis of spin of the fluid particle at each point. In two dimensions, the vorticity is the sum of the angular velocities omega A and omega B of any pair of mutually perpendicular fluid lines AA and BB passing through the point in question. In a rigid body, every line has exactly the same angular velocity. So the vorticity of a rigid body is the same at every point. It is exactly twice the angular velocity. This gadget is a vorticity meter, which floats in water with its axis vertical. The two vanes at the bottom are driven by the angular velocities of two mutually perpendicular fluid lines. So the arrow at the top turns at a rate equal to the average of these two. That is, with half the vertical component of vorticity of the lump of water in which the vanes are immersed. This tank has been on the turntable for a long time, and viscosity has forced the water into a rigid body rotation. Of a spiral vortex tank, water passes from the reservoir through a flow straightener and into the tank through a tangential entry. It spirals round and round in a very tight vortex and finally leaves vertically through a drain in the center. What will the vorticity meter do? It doesn't rotate. It moves in pure translation, like the needle in a compass box mounted at the rim of a rotating turntable. Let's look at a fluid cross as it goes round the vortex. Leg A follows the streamline, so it rotates counterclockwise. The angular momentum of the fluid is conserved as it flows toward the drain, so the tangential velocity varies inversely with the radius. This means that the velocity of the inner part of leg B is greater than the velocity of the outer part, and so leg B turns clockwise. The clockwise turning rate of B is just equal and opposite to the counterclockwise turning rate of A, and so the net vorticity is 0, and the vorticity float confirms this. Incidentally, since the two vanes of the float are rigidly connected, the float does not respond to the shear deformation of the two fluid lines, but only to their average angular velocity. There are several theorems which relate the vorticity to the dynamics of fluid flow. One of these is Crocco's theorem, which is nothing but a special form of the dynamical equations of motion. With steady motion, if the flow is incompressible, if there are no viscous forces, and if only conservative body forces are present, then the vector product of the velocity vector with the vorticity vector is equal to the gradient of the stagnation pressure divided by the density, where the stagnation pressure, or as it is sometimes called the Bernoulli number, is the sum of the static pressure and the dynamic pressure and the pressure associated with the body force field. Consider a two-dimensional flow in the plane of the paper. If the flow is two-dimensional, the vorticity float rotates almost exactly with the speed of the crossed white lines on the bottom of the tank. Sometimes the word rotation is used as a synonym for vorticity, but this does not mean that a flow has to be curved for vorticity to be present. Here, for instance, water flows in a straight channel. The streamlines are essentially straight and parallel to the side wall. But the arrow rotates, showing that vorticity is present. Near the wall is a viscous boundary layer, in which the velocity increases with distance from the wall. Let's look at a fluid cross. One leg moves downstream parallel to the wall, while the other leg rotates because of the non-uniform velocity distribution. So there is a net vorticity, and the vorticity meter spins. On the other hand, the flow may be without rotation, even though it is curved. This is the plan view